We're going to continue our discussion about kinetics with the rate law. We're going to be talking about the rate law. It's an equation that helps us relate how fast a reaction occurs when we take into account its concentrations. And these concentrations are raised to some power. And the rate law lets us know how fast it could go. We can predict how fast. It can tell us the steps of a reaction, and we can also find the orders of the reaction. All right, now when we're talking about rate law, we can talk about how products are formed or how reactants are used up. We are going to ignore the products, and in order to ignore the products, what we need to do is to look at reactions and study them at the instant they start. So we're looking at the instantaneous rate when you mix two things together. We're going to be talking in this section about the differential rate law. That tells us how the concentration of the reactants, this is really important, the concentrations of the reactants affect the rate of the reaction. Let's say we have this general equation where the small letters are the coefficients, the large letters are the species or the chemicals. The rate law has this form. The initial rate is equal to K, which is the rate law constant, times the concentration in molarity of the reactant raised to some power that must be determined experimentally and is not the coefficient, times the concentration of B also raised to some power. We call these powers orders. Please note they are not the coefficients. Okay. K does not depend on the concentration. The only thing that affects K is the temperature of the reaction. So let's define some more stuff. The reaction order are those exponents. The order in A refers to this exponent. The overall order would be all of the exponents added together. So if we had this synthesis reaction of water, the rate has been experimentally determined to be rate is equal to the rate law constant times H, the concentration of hydrogen raised to the first power. Please recall that chemists are very unhappy about writing the number 1. It's there, we just don't write it. Times the concentration of O2 raised to the first power. 1 plus 1 equals 2. The overall order is 2. This rate law has an overall order of 3. 1 plus 2 is 3. Let's see what this overall order means. If the order of the reaction is 1, whatever the rate does, whatever the reactants do, the rate does. So if you double the reactants, then the rate would be double. If the order of the reaction is 2, then if you double the reactants, you quadruple the rate. So if I were to look at this reaction, if I doubled the rate of if I doubled the concentration of HCl, I could expect the rate to double. However, if I doubled the concentration of NH3, I could expect that to quadruple the rate. Okay. Now, the big trick about the rate law constant is the units of the rate law constant. It is a code that chemists use to gather information. We are talking about, remember, concentration in terms of molarity. Molarity is equal to the moles of the solute over the liters of solution. We can write that as M. We can write that as moles times liters to the -1. We can write that as moles per liter. Doesn't matter to me. I prefer to use this because I am lazy. Right? A rate is the change in concentration, so that would be change in molarity per unit time. Mostly, these are in seconds. So by knowing the rate law constant unit, you can tell a lot about the order of the reaction. So this is how it works. You take the overall order, so you have molarity, let's say the overall order is 2, subtract 1 minus the overall order, and multiply it times the time unit, I'm using seconds as an example, to the negative 1. Let's recall that would be the same as writing it per second. So the rate law unit would be 1 minus 2 is negative 1 times second to the negative 1. Very frequently, you will only be given the unit of the rate law constant, and they will expect you to figure out the order of the reaction. Okay, let's look at this. What's the overall order for this reaction? 1 plus 2 is 3. What are the rate law constant units for this reaction? The unit for this, if it were in molarity per second, would be m1 minus the overall order, 3, times seconds to the negative 1. That would be m to the negative second times second to the negative 1. The overall order here is 2. That would be m1 minus 2 times second to the negative 1. We would simplify that to this expression. What happens if it's first order? If it's first order, it would be 1 minus 1 times second to the negative 1. This would drop out, and you would either write it as second to the negative 1 or 1 over second. I'm going to skip this problem to go to this third problem, which is a little more interesting. Right? Given this reaction, determine the rate law. Before we can determine the rate law, we need to find the order of each one of the reactants. I said before that the the order can only be determined experimentally. Here's an experiment run 3 different times, where the experimenter very wisely changed one variable at a time. For the first trial, she had these values and got this rate. In the second trial, this person doubled the rate of NO while keeping O2 constant, and we can see what happened to the rate. And that's what we're looking at. So we will figure these out in this fashion. To figure out the order of NO, I need to inspect 2 trials where NO changes, but O2 doesn't. That's the only way I can be sure that NO is affecting the rate and not O2. We can see that would be trial 1 and 2. To make things easy, I'm going to put the big numbers on top, trial 2 over trial 1, and I simply write the general rate law form. So rate 0.0164 in trial 2 is equal to the rate law constant times the value of NO in this trial raised to some power, I'm going to call it N, times O2 raised to some power, and I'll call that N. In trial number 1, the rate is 0.0041, and that's equal to the rate law constant. This time, the value of NO was 0.03 raised to some power, while the O2 remained the same. We can see that these cancel and these cancel. Here, 0.0164 divided by 0.0041 is 4, is equal to 0.06 divided by 0.03 is 2, raised to some power that is m. m, 2 raised to what power is 4? Well, m obviously is equal to 2. So the order of NO determined experimentally is 2. Now, in order to find the order of O2, I need to keep the NO constant while the O2 is changing, so I can see what effect that will have. And in this case, I can see that trial 3 versus trial 1 will suit my needs. And O stays the same while O2 changes. So trial 3 versus trial 1. So trial 3 has a rate of 0.0082 molarity per second, and that is equal to the values of NO that we now know is raised to the second power times the value of O2, whose power has yet to be determined, whose order is yet to be determined. And when we look at that in comparison to trial 1, we see these values. This will drop out, this will drop out, this number divided by that number is 2. 0.04 divided by 0.02 is 2. So the order of O2 is n. 2 raised to the first power is equal to 2, so the order of O2 is 1. So the rate law for this is the rate of this reaction is equal to the rate law constant times the concentration of NO raised to its order 2 times the concentration of O2 raised to its order 1. And we don't generally write ones. Now, let's determine the rate law constant. Choose any trial and use the data and substitute into the rate law. I choose 2. So the rate is 0.0164, and that is equal to K, when the value of NO is 0.06 raised to the second power, and the value of O2 is 0.021 raised to the first power. When I do my math, I come out with 0.0164 divided by 7.2 times 10 to the negative 5th, which is this squared times that, is equal to K. K is equal to 228. Now remember, the rate law constant is has that very important unit. It is in terms of molarity, so we know that it is molarity 1 minus the overall order. The overall order is 3, so it is to the negative 2, and that would be per second.